6, Newton's second law in rotational form. This is daily video 2, where we're going to conduct an experiment to help us understand the relationships between angular acceleration, torque, and rotational inertia. I'm Wes Taylor, and I'm a physics teacher at Walton High School in Marietta, Georgia. So here's the lab setup that we're going to use to figure out the relationship between angular acceleration, torque, and rotational inertia. My rotating system is going to be this bar with these two brass masses that are at the end. Now, I can adjust the position of these brass masses by loosening this screw and sliding them around. They pivot about this point in the center. Now, all of this is connected to a rotary motion sensor. The data from this will allow me to determine the angular acceleration at any point in time by graphing angular velocity versus time and finding the slope of that graph. So the rotary motion sensor will allow me to directly measure the angular acceleration of my rotating system. The rotational inertia comes from measurements of the positioning of these brass masses along this rod. And then finally, for the torque, the rod is sitting on top of a pulley system. So it's very difficult to see here, but I have a string that's wrapped around this pulley. It then comes over a secondary system and down to a force sensor. So if I allow this to hang, this force sensor will read the tension in the string. And then that string, where it's wrapped around that pulley, will provide the torque that allows my system to rotate. So for this first setup, I'm going to leave my masses at the furthest position so that I have a constant rotational inertia. To change the torque, I'm going to hang masses from my force sensor. So here's my force sensor, and I have an example of one of my hanging masses. I will hang that there. I've now increased the tension in the string and therefore the torque that's exerted on the rotating system. For this first lab, I'll continue to add masses, increasing the value of the force reading, which means I'm increasing the value of the tension and therefore my torque. So here you see all of the data that I collected for this first iteration of the lab. So I had to find the mass of each of those brass masses, and R brass is the distance from the center of each of those brass masses to the axis of rotation. Those pieces of information I can use to determine the rotational inertia for the two brass masses and how that affects the system. Then I took the mass of the rod and the length of the rod. Those two numbers will be used to calculate the rotational inertia of the rod itself. And then finally, I used a set of calipers to measure the diameter of the pulley where the string was wrapped around. Half the diameter gives me the radius, and that's the distance I'm going to need to use when I'm calculating the torque provided by the tension in the string. That's one common error that I've seen students have when working this lab. So, to get an initial understanding of the rotational inertia of my system, I need to add the rotational inertia of each individual component. That means the rotational inertia of brass mass 1, of brass mass 2, and the rotational inertia of the rod. We can treat those brass masses as point masses, so the calculation for rotational inertia is just mr squared. Now, for a rod of uniform mass distribution that is rotating about an axis through its center, the calculation comes out to be 1/12 the mass of the rod times the length of the rod squared. Plugging in my numbers, that gives me an initial value to use for the rotational inertia of this system, and that's the value that we're going to keep constant for this first iteration. Now you can see in the data table, I continuously added mass to my force sensor so that it provided a greater and greater tension force to pull on the system. I calculated the torque using that force times the radius of the pulley that the string was wrapped around. And then I was able to get from the rotational motion sensor data the angular acceleration for each of these trials. Now, let's practice analyzing this data. Here we see a graph of our angular acceleration versus our torque. Now, when I'm looking at this data, It appears to be a linear relationship, which for data analysis in this class is wonderful. That means I can go straight to drawing a line of best fit. Once I've done that, that tells me that the value on my y-axis is directly proportional to the value on my x-axis, meaning, in this case, with constant rotational inertia, the angular acceleration is directly proportional to the torque exerted on the system. So for this second experiment, I want to keep the torque applied to my rotating system constant. So I've picked one of my masses to hang from my rotary force sensor, and I'm going to leave that as the sole source of the tension and therefore the torque on my system. I'm going to change the rotational inertia for this second section. So I've already got my data for the masses in this position. If I loosen them and move them in 1 centimeter at a time, that will provide a new rotational inertia for this rotating system. I'll do that multiple times to collect data where I've got angular acceleration readings for changing rotational inertia while the torque on the system is being kept constant. So now that we've adjusted our setup, here's my new data set. You can see along the left side of the chart that I have taken my brass masses and incrementally brought them in about 1 centimeter at a time towards the axis of rotation. I've gone back through the rotational inertia calculations that I showed previously, and then I've measured the angular acceleration. All of this while always providing the same or constant torque to the system. When I go to analyze this data, I'm going to do angular acceleration as a function of rotational inertia. This graph is not linear. In fact, it appears to be inverse. This looks very much to me like an inverse curve. So how do we go about analyzing this data to find the relationship between angular acceleration and rotational inertia? We've got to linearize. So when we're going to linearize our data, this is what we do if we see a nonlinear relationship when we first plot the data from our experiment. To start, we have to check and see, does the data appear to fit any of the common relationships? Inverse, a squared relationship, an inverse squared, or square root. These are all relationships that you might see in this course. Once you've identified which of those relationships it looks like it might be, then you need to calculate new values to plot on your x-axis. Now for us, I said that that curve looked like an inverse curve. So what that means is I need to take my x-axis values, which in this case were my rotational inertia values, and I need to calculate the inverse of those values. So you see here in my center column, I've done just that. So now, to check to see if I found the correct relationship, I'm going to plot angular acceleration versus my new calculated values for the inverse rotational inertia value. Here we see those values plotted. That is a linear relationship, which means I've hit on the correct relationship between my variables. I can draw my line of best fit. And this shows that the angular acceleration is not proportional to the rotational inertia. It's proportional to the inverse of the rotational inertia. So if we look at the analysis of both of these parts of the lab, together they show us that the angular acceleration is directly proportional to torque and inversely proportional to the rotational inertia. Looking at each lab's data set, we can try to find a physical meaning or value for the slope of those graphs. In our first lab, we did angular acceleration versus torque while keeping the rotational inertia constant. When we find the value of the slope and take its inverse, we find the value is 0.00505 kilogram meter squared. That's remarkably close to the constant rotational inertia value we set for that part of the lab, 0.00525 kilogram meters squared. So what that tells me is that the slope of that line is, in fact, the inverse of the rotational inertia. In the second lab, we kept our torque on the system constant while varying the rotational inertia. So we graphed angular acceleration versus the inverse of rotational inertia. We calculate the slope of that line. It comes out to be 0.0089 Newton meters, which is again incredibly close to the constant torque value we had applied of 0.0091 Newton meters. What does this all tell us? Well, the graphs themselves showed us proportionalities, but by proving the values of the slopes were more or less equal to the values of the constants or the inverse of the constants that we were applying, we can show that the actual equality is that the angular acceleration is equal to the net torque divided by the rotational inertia. And this is where Newton's second law for rotating systems is put into equation form. So what should we take away from this? Experimental analysis will show us that there is a direct proportionality between angular acceleration and torque, and an inverse proportionality between angular acceleration and rotational inertia. Collecting data from these labs allows us to write the full equality for Newton's second law for rotating systems. The angular acceleration of the system is equal to the net torque of the system divided by the rotational inertia of the system. Thanks for watching.